In this lesson, we will learn how to solve systems of equations involving linear and quadratic functions, and we will analyze the solutions. Now, looking at solving linear quadratic systems, we want to recall what is a system of equations? Well, a system of equations is a set of two or more equations. So when we looked at linear systems, both equations were linear. Today's lesson, we're looking at a system of equations where one function is linear, the other is quadratic. Now, recall, what is a system of equations? System of equations is a set of two or more equations. Consistent system if there exists at least one common solution in the set of real numbers. The solution set of a consistent system can be found using graphical method and or an algebraic method. So, key concepts. Linear quadratic system is a system that consists of a linear function whose graph is a straight line and a quadratic function whose graph is parabola and two variables. Now, looking at a set of real numbers, a linear quadratic system may have three different solutions. The first would be you can have two solutions. That means the line h at x, which is your linear function, is the secant line to the function f at x, your quadratic function. And what that means, the secant line means that the linear function touches the quadratic function at two distinct points. That is a special name called a secant line. If you have your second option, instead of two solutions, one solution, that means that linear function is now a tangent line because it intersects the quadratic function at exactly one point. So the line h at x is a tangent line to the function f at x. However, you can have a scenario, which is your third one, where there's no solution. That means that line h at x, that linear function, never intersects the quadratic function. So we're going to explore solving linear quadratic systems graphically. So we're going to have to bring back our skills of graphing. In example one, we're going to graphically determine the solution to the system. So we want to see with our linear system, will we have two solutions? That means the linear function would be a secant line to the quadratic function. Or will we have one solution where your linear function will be the tangent line to the quadratic function, or no solutions? That means the linear function never crosses the quadratic function. So let's start by bringing back our graphing skills. And if you notice f at x, we're going to graph them both and see where they cross and how many times they cross, if at all. So f at x is equal to x squared, which means that's our parent function. And we know those key points is -2 and 4, -1 and 1, 0, 0, 1, 1, 2, and 4. Right, so graphing that, and -2, we're at 4, and -1, we're at 1, 0, 0, 1, 1, 2, and 4. And just to make my parabola nice and clear, I'm going to add in that additional point. Nice, smooth curve. And that would be labeling properly, of course, always. Okay, so that's our linear quadratic function. G at x would be our linear function, and we have x plus 6. Now it's in slope y-intercept form, so we're going to identify the number in front of x is your slope, which is 1. We don't see it, but we know it's there. So it's 1 over 1, so it's going to be rise over run, and my y-intercept is 6. So when graphing that linear function, we start at the y-intercept of the 6, we rise 1 over 1, rise 1. And if you notice, we do end up crossing at one point for sure. Now again, linear function in the opposite direction. All right, so we notice it does cross at 2 points. So therefore, this linear function is a secant line to the quadratic function. So I'm going to quickly just connect that with the ruler. If we do that. Okay, so to properly identify that as well, I'm just going to, okay, so the first point here, which is that x is -2, and y happens to be 4. And the other point here, x is 3, y is 9. Okay, so therefore, don't forget your therefore statement. So therefore, the solution or we're going to say, or point of intersections to the system are, and from left to right, we're going to say -2 and 4 and 3 and 9. So we also can say, therefore, G at x is the secant line to f at x, right? Because it does cross it at two distinct points. Excellent. So that's how we would solve a linear quadratic system graphically. Okay, moving on, we're going to learn how to solve that linear quadratic system algebraically, and we're going to follow the following steps. So the method we're going to use is step one. If the system is in function notation, which it often is, we're going to set both equations equal to y. So we learned earlier that f at x is another way of recognizing or identifying that y is equal to f at x. So we're going to change that notation so that it is in the form y equals. Then we're going to solve for y or x in the linear equation if necessary, meaning we're isolated, starting with the linear function, we're isolating for either x or y. Once we do that, we're going to substitute that simplified equation into the quadratic equation. From there, we're going to isolate for x or y, solve for each of them. Now, sometimes we'll have to use factoring, we might use completing the square, or use the quadratic formula. Once we have done that, we know, even when we look at the solutions graphically, each point has an x coordinate and a y coordinate. So if you've solved for the x coordinate, we're going to sub it back into the linear function to find the corresponding y coordinate. So looking at example 2, let's find the coordinates of the points of intersection for the given system. Verify with a quick sketch. So we have, notice the notation is m at x is equal to x squared minus 6, and n at x is equal to 2x minus 3. So the first thing we're going to do is express both the function notation in terms of y. So we're going to say y is equal to x squared minus 6, and y is equal to 2x minus 3. Okay, now we learned from solving linear quadratic systems graphically that the point of intersections, the x and y values are the same. That means that point exists on the linear function as well as the quadratic function. So with that in mind, the y's would be exactly the same. And y is already isolated for here. So we can say, therefore, y is equal to y. That means x squared minus 6 has to equal to 2x minus 3. So the y's are equal both in that quadratic function as well in the linear function. So we've made them equal to each other, and now we're going to simplify and solve for x. So we have x squared. We're going to bring that 2x over, so minus 2x minus 6 plus 3 has to equal to 0. So we have x squared minus 2x minus 3 is equal to 0. So we've simplified to a quadratic equation. This quadratic equation is a simple one because if you look at the coefficient in front of x squared, it's just 1. So we can simply factor that simple trinomial. The sum is that middle term, which is -2. Product is equal to -3. Simplifying, we have -3 and +1. Because -3 times 1 is -3, -3 plus 1 is -2. So we're going to set up our double bubble. X is the first term in each bracket, and then we input the values, the numbers that satisfy both the sum and the product. From there, we can solve for x. We set x minus 3 equals 0, x plus 1 equals 0, and solve for x. So x is equal to +3, or x is equal to -1. So just from this, we see that there are two solutions. So that linear function, n at x is going to be a secant line to the quadratic function m at x. So we've isolated, we got x for each. Remember, we need the corresponding y coordinate. Now, we can technically even substitute into the quadratic function, but typically we stick with the linear because it's simpler. So we have, for the linear function, y is equal to 2x minus 3. So we substitute. We saw that x is equal to 3, so we're going to substitute that into our function, and we're going to notice that y is equal to 2 times 3 minus 3. Y is equal to 6 minus 3. Y is equal to 3. So I'm just going to show you if we decided, because you like working with the quadratic function, if we substitute that x value into, and you don't have to do this more this once, you don't have to show both. Our point of intersection in this case is x is 3, y is 3. Okay, but let's just quickly to the side here, or if I put it in the equation y is equal to x squared minus 6, you'll notice substituting 3 squared minus 6, 9 minus 6, y is still equal to 3. Okay, so it doesn't matter which one you sub it into, but I prefer to just put into the linear function. So let's do that here. So we have y is equal to 2x minus 3. Y is going to equal to 2 times negative 1 minus 3. Y is equal to negative 2 minus 3. Y is equal to negative 5. So therefore, and 2 points of intersection, negative 1 and negative 5. So we're going to quickly do a sketch to verify those are the points of intersections. Okay, so let's do that before I let statement. So we have y is equal to x squared minus 6. So quickly we know that's the parent function. It has a vertical translation down 6 units. So 0, 0 would be here, here, and here. Oops. And then, okay, so we just take the parent function down 6 units, and that would be our m of x, which is equal to x squared minus 6. Okay, so looking at that linear function, we know that slope start with the y-intercept of negative 3, then the slope is 2, so we're going to go up 2 over 1, up 2 over 1, up 2 over 1, and look at that, down 2, and there we have it. Okay, so then taking out our ruler, connecting those. Mm-hmm. 3 and 3, negative 1. Negative 5, and that again is 3 and 3. So we've actually proved it graphically as well. So we can say, therefore, the points of intersection for the given system are negative 1, negative 5, and 3 and 3. That is, we know that nx is a secant, oops, sorry, let's get that back there, that we said, n at x, that is, n at x is a secant line to m at x, to the function m at x. Excellent. So with that in mind, when we solve this linear quadratic system, whether it's graphically, whether it's algebraically, you have 3 possible solutions. Now, we can actually determine that based on something called the discriminant. The discriminant can also be used to determine the number of solutions to a linear quadratic system. When using the discriminant formula, if the discriminant d is equal to b squared minus 4ac happens to be greater than 0, then the linear quadratic system has exactly 2 solutions. If, however, we find the discriminant, so that value of b squared minus 4ac is actually equal to 0, then the linear quadratic system has only one solution. If, however, we find the discriminant b squared minus 4ac is less than 0, then the linear quadratic system has no solutions. Okay, so we're going to use a discriminant to determine the number of solutions of the following systems. Now notice in each system, we have a quadratic function, we have a linear function. Now, in order to use that discriminant, you do have to set them equal to each other and then come up with that quadratic equation. Based on the quadratic equation, you determine your discriminant. Okay, so a is always that variable in front of x squared, b is front of the variable in front of your x, and your constant is always c. So with that in mind, let's start with the first example, 3a, where f at x is equal to 3x squared minus 2x minus 4, when g at x is 3x plus 5. So we always let f at x equal to g at x. Okay, so in this case, it would be 3x squared minus 2x minus 4 is equal to 3x plus 5. So in this case, it's f at x and g at x, but you let the two functions equal to each other. And then you create a quadratic equation. So we're going to take 3x squared minus 2x. We're going to bring over that 3x, so minus 3x minus 4 minus 5 is equal to 0. Again, silly mistakes happen when we forget to change the sign when you take something from one side of the equation to the other. So fully simplifying here, we have 3x squared minus 5x minus 9 is equal to 0. So as you can tell, that would be your A, this would be your B, and that would be your C. Okay, so we determine the discriminant. Again, if it's greater than 0, we know we have two solutions. If the discriminant value is equal to 0, there's only one solution. And if it's less than 0, there are no solutions. So with that in mind, we can say discriminant is equal to b squared minus 4ac. So d is equal to negative 5 all squared minus 4 times 3 times negative 9. So always following BEDMAS. Negative 5 is 25, then negative 4 times 3 times negative 9, which is a positive 133. D is equal to 158. Now that value definitely is greater than 0. So we can say, therefore, since D is greater than 0, the system has two solutions. Okay, it doesn't tell us what those point of intersections are. It just tells us how many solutions this quadratic linear system would have. So looking at B, same idea. We're going to say now h at x is equal to k at x. And we're going to say negative x squared plus 3x minus 5 is equal to negative x minus 1. Again, I always want to make sure that the a value of the quadratic equation is positive. So I'm going to move everything over to the right side. So 0 is equal to x squared. So we have minus x minus 3x minus 1 plus 5. Again, silly mistakes happen when we bring something from one side of the equation to the other and we forget to change the operation. So 0 is equal to x squared minus 4x plus 4. So the discriminant in this case, again, remember the number in front of x squared, this is your a, so a in this case is 1. I should have written that. B is equal to... Okay, so b is equal to negative 4, and c is equal to 4. So substituting b squared minus 4ac, discriminant would be negative 4 all squared minus 4 times a times c. So d is equal to negative 4 squared, which is 16, negative 4 times 1 times 4, which is minus 16. So d is equal to 0. So therefore we can say, since the discriminant, capital D, is equal to 0, the system has one solution. Continue on with C. Again, we let P at X is equal to Q at X. We have negative 2x squared plus x minus 3 is equal to negative x minus 2. I would bring everything over to the right. So 2x squared minus x, bring that plus x over, minus x minus 2 plus 3. So we have 2x squared minus 2x plus 1. And then, so that means a is equal to 2, b is equal to negative 2, and c is equal to 1. So we have d is equal to b squared minus 4ac. D is equal to b, which is negative 2 all squared, minus 4 times 2 times 1. So we have d is equal to 4, negative 4 times 2, which is negative 8 times 1, which is minus 8. So d is equal to negative 4. Now, since the discriminant is less than 0, we can say, therefore, since d is less than 0, the system has no solutions. So the discriminant tells us a lot about our linear quadratic system. It will tell us how many different solutions we have, whether it's 2, 1, or none. Okay, moving on to number 4, we have what values of the slope that will make g at x is equal to mx minus 5 tangent only one point of intersection to the following function f at x is equal to 3x squared plus 4x minus 2. So that means if there's only one point of intersection, so one solution, we know that the discriminant has to equal to 0. Okay, so I'm going to make a little note. So tangent line, so tangent equals 1 point of intersection. Therefore, d has to equal to 0. Okay, and that's going to help us out because that'll help us solve. So we're going to let the two functions equal to each other in order for us to determine that discriminant. So we're going to say f at x has to equal to g at x. Just like we did above, but this time we have an unknown we have to solve for. So 3x squared plus 4x minus 2 is equal to mx minus 5. Following what we did above, we need a quadratic equation first before we can determine that discriminant. We're going to say 3x squared plus 4x minus mx minus 2 plus 5 has to equal to 0. So fully simplifying, we have 3x squared. We can factor out that x. We're going to have 4 minus m. And then negative 2 plus 5, which is positive 3, has to equal to 0. So in this case, we're dealing with an expression for b. So a is equal to 3. B this time is equal to 4 minus m. And c is equal to 3. Now, we already mentioned because it's a tangent, that means there's only one solution. That means the discriminant has to equal to 0. So d equals b squared minus 4ac. We know that d has to equal to 0. So we're going to say 0 is equal to b, which is 4 minus m, all squared, minus 4 times a times my c. So 0 is going to equal to, now remember that's a binomial square. So we're going to remember to expand that. Square the first term, which 4 times 4 is 16. 2 times those two terms multiplied together. So 4 times negative n times 2, which is negative 8m. And then we have negative m squared. So m times m, which is m squared. And then 4 times 3 is 12. 12 times 3, which is minus 36. Okay, so simplifying here, we have m squared minus 8m, 16 minus 36, which is minus 20. So in this case, again, it's a simple trinomial. So the sum is equal to negative 8. The product is equal to negative 20. So I know negative 10 times 2 is negative 20. Negative 10 plus 2 is negative 8. So factoring this fully, we have double bubble. M is the first term in each bracket, and then the numbers that satisfy the sum and product would be the second terms. The order does not matter. So in this case, then we still need to isolate. We're going to say m minus 10 is equal to 0, or m plus 2 is equal to 0. So either m is equal to 10 or m is equal to negative 2. Okay, so that was the slope that would make that linear function a tangent line to the quadratic function would be if m is 10 or if m is negative 2. So therefore statement, don't forget that always, the slope values of m is equal to negative 2 or m is equal to 10 will make g at x tangent to f at x. One, moving forward, we have a word problem. So we have a skydiver jumped from an airplane and fell freely for several seconds before releasing her parachute. Her height, h in meters above the ground at any time, is given by the following. H at 1 t is equal to negative 4.9 t squared plus 5,000. Before she released her parachute, height. H at t is equal to negative 4t plus 4,000 after she released the parachute. We need to determine A, how long after jumping did she release her parachute to the nearest tenth of a second? And then we need to find out how high was she above the ground at that time to the nearest tenth of a meter. So we basically have to find this intersection point because they're asking us for that specific point. So we know the time at the height that this all happened. So with that in mind, we're going to let both functions equal to each other and then solve for t. Once we know what that t is, we can sum it back to either of the functions, whether it's the quadratic, I prefer the linear, to figure out the corresponding height would be. So the time it happened and at what height was that at. So let's start with A. We're going to say, we're going to let h1t is equal to h. Now, earlier we look at the methods when it says to solve. Right away, when you have decimals, you know you're going to probably be using the quadratic formula. So we're going to let negative 4.9 t squared plus 5,000 equal to negative 4t plus 4,000. Now again, I always like for the a value to always be positive, so I'm going to move everything over to the right. So 0 is going to equal to 4, and always in decreasing order, of course. So we're going to say minus 4t, we're going to say plus 4,000 minus 5,000. Okay, again, reminder, when you bring something from the one side equation to the other, change the operation. To simplify, we have 4.9 t squared minus 4t minus 1,000. Okay, so we're going to use the quadratic formula. Anytime there's a decimal, it's not usually factorable, but we know A is equal to 4.9, B is equal to negative 4, and C is going to equal to negative 1,000. So with that in mind, we know T, that's where how long means time. Okay, so we're going to say t is equal to negative b. So we're going to say negative 4 plus or minus b squared minus 4. Oops, I put b squared and I wrote 4.9, so I meant to write negative 4 all squared minus 4 times a, which is 4.9, times c, which is negative 1,000, all over 2 times a, which is 4.9. Right, so simplifying, we have t is going to equal to positive 4 plus or minus, and taking out our calculator, 4 squared minus 4 times 4.9 times 1,000, which is going to equal to, and we take the square root of that, putting that all into our calculators, you should, and because nearest tenth of a second, we'll round at the very end, but to all over 9.8, we're going to get t 1 is equal to 4 minus 140.06 divided by 9.8, you would get negative 13.9, which we know as time, that's negative time you can't have. It might satisfy the equation, but it does not satisfy our situation. So this is called inadmissible. It means it doesn't apply to our problem. Or we can have T2, where we take 4 plus 140.06 and divide that by 9.8, and we would get about 14.7 seconds. Right, so remember, sometimes when we solve the quadratic equation using the formula and even factoring, one of the values might not be something we can use. That's what inadmissible means. We can't apply it to our problem because you can't have negative time. So we can say therefore, how long after? So about, because we did approximate, 4.7 seconds after jumping, she released her parachute. Now, if you like to use approximately, you can use that well or about, either one. Now, B, we want to figure out, again, how high was she above the ground at this time? So we can substitute, it doesn't matter which, again, equation. I prefer always to use the linear, so we're going to sub it into that one, 14.7. Now, again, this is also approximated because we did round the time plus 4,000. Which is equal to, putting that into our calculators, negative 4 times 14.7 would be negative 58.8 plus 4,000. Now, again, like I stressed earlier, it doesn't matter. We could have simply substituted that value of time into the quadratic function. You will still get the same height. So about, we're going to say 3,941.2 meters. So therefore, at this time, she was about 3,941.2 meters above the ground. Okay, moving along to example 6, we're going to determine the point at which the circle given by the following x minus 5 all squared plus y minus 5 all squared equals 25 is intersected by the following line, negative 6x plus 6x, negative 7x plus 7y is equal to negative 7. Verify with a sketch. Okay, so in this case, it's we want to make sure, we want to see where they cross. So the circles are given to us, which is excellent. We want to determine at which points they intersect. So with that in mind, it would be probably best to isolate again with your linear function. So we have negative 7x plus 7y is equal to negative 7. Okay, so let's simplify that. We are going to have to divide everything by negative 7. So x minus y is equal to 1. Okay, excellent. So with that, we need to isolate for one of the variables. Now, in this case, because x is always positive, we're going to bring that over. I'm going to say x is equal to 1 plus y. Okay, with that in mind, now we can substitute where we see x in the circle equation. We can figure out, or we can substitute where we see x, we're going to replace it with 1 plus y. So let's do that. So let's substitute. Circle equation in order to find out where they cross. So we have x minus 5 all squared plus y minus 5 all squared has to equal to 25. So where is x? I can put 1 plus y. Oops. minus 5 plus y minus 5 is equal to 25. Okay, so that becomes y1 minus 5, which is minus 4, all squared, plus y minus 5 all squared is equal to 25. Okay, so with that, again, a binomial square, we're going to actually use, remember when we did factoring, but now we're expanding that. So it's a binomial squared becomes a perfect square trinomial. So we square the first, which is y squared. 2 times those two multiply together. So negative 4 times y is negative 4y times 2, which is negative y, and then negative 4 squared, which is 16. Likewise, y squared, 2 times those two multiply together, plus 25 minus 25 has to equal to 0. Okay, we want to create that quadratic equation, and with that in mind, we would have we would able to factor that, or maybe we might have to use the quadratic formula to solve. So we have y squared plus y squared, which would be 2y squared. We have negative 8y minus 10y, which is negative 18y. Those 25s cancel, so we have plus 16 has to equal to 0. And again, we can divide. You want to simplify as much as possible. So this becomes y squared minus 9y plus 8 has to equal to 0. Simple trinomial, so sum is equal to negative 9, product is equal to 8. So it's going to be negative 8 and negative 1. So y minus 8, y minus 1 has to equal to 0. Y minus, 8 has to equal to 0, so y is either equal to 8, y minus 1 is equal to y is equal to 1. So we have the y coordinate, we need the corresponding x coordinate. We know x is equal to 1 plus y. So from this, we can tell that in this system, actually it's not linear, and we have the circle, that the linear function will cross that circle twice at 2 points. So then x is equal to 1 plus 8, x is equal to 9. So the first point of intersection would be 9 and 8. Remember, x comes first, then y. And then we can say x is equal to 1 plus y. X is equal to 1 plus 1. X is equal to 2. So in this case, x is 2, y is 1. Okay, so therefore, the line intersects the circle at 2 points, 2 and 1, and 9 and 8. Okay, so verify with the sketch. Well, if we have x is equal to 1 plus y, we're going to rearrange that to equal to 1 equals x minus 1. So my slope is equal to 1. My y, which is a negative 1. So rise over run. So we'd start at negative 1. And we'd rise 1 over 1, rise. Oh, there's the first. Then we keep going, rise, run, rise over run, rise over, and yeah, as we determined. Let's just graph that quickly. Negative 7x minus 7y is equal to negative 7. And we see those 2 points of intersection. 2, 2 and 1, and the other one is 8. 9 and 8. 9 and 8. And there you have it.